Thunderstorms and wind shear have caused more aircraft accidents than nearly any other weather phenomenon. This curriculum, covering life cycles, cell types, and warning systems, forms the core of your DGCA Paper 2 exam because understanding these dynamics is a prerequisite for safe flight operations. Imagine an aircraft on final approach. The skies immediately ahead and below the aircraft are perfectly clear. The glide path looks completely safe. But 15 miles away, a massive cumulonimbus cloud is actively venting out an anvil of ice crystals. Without warning, massive hail drops from that overhanging canopy directly onto the descending aircraft. In the presence of convective weather, visual meteorological conditions mean very little. A clear line of sight does not equal a safe operating environment. To survive these encounters and to pass your meteorology exams, you have to understand the internal kinematics of the storm, specifically the massive vertical air drafts powering it. You must completely abandon reliance on what you can see out the windshield and instead build a precise mental model of the storm's unseen, expanding threat envelope. Every thunderstorm is driven by a single thermodynamic engine, the convective updraft. This animated diagram shows the first phase, the cumulus, or developing stage. For 10 to 15 minutes, strong updrafts surge through the cloud, represented here by the red vertical arrows. There are no downdrafts yet, and no precipitation has reached the surface. As the cloud builds, it enters the mature stage, which lasts 15 to 30 minutes. Notice the downward-pointing blue arrows appearing alongside the red. Precipitation has now become heavy enough to fall against the updraft, dragging cold air with it to the surface, while the top of the cloud spreads out into an icy anvil. Looking at this kinetic structure, which of these stages is the most dangerous for an aircraft, and what exact mechanical factor makes it so? The mature stage is the deadliest. It contains extreme vertical wind shear because massive updrafts and violent downdrafts are shearing directly against each other simultaneously. Eventually, the storm exhausts itself and enters the dissipating stage. The red updraft arrows vanish. Downdrafts now dominate the entire structure, choking off the storm's energy supply as the precipitation visibly thins out and the cell slowly dies. An isolated single-cell thunderstorm completes its hour life cycle in about 30 to 60 minutes. But storms rarely remain isolated. They organize into broader, more persistent structures. This radar map shows a multicell storm. It is a persistent cluster of individual cells at varying stages of development. New cells continuously develop on the upwind flank to replace the older dissipating cells. Even though one cell dies quickly, the system as a whole can persist for hours. The most dangerous and highly organized structure is the supercell. The cluster clears, replaced by a single, massive cell dominated by a rotating updraft called a mesocyclone. It maintains a quasi-steady state for hours by constantly ingesting fresh, unstable air. Supercells are the exclusive source of violent tornadoes and extreme hail. While tornadoes are rare in regions like India, their mechanics remain highly examinable. Finally, when instability is pushed ahead of an advancing cold front, you get a squall line. This unbroken horizontal wall of severe weather can extend for hundreds of miles, creating a continuous boundary of turbulence and wind shear. Identifying the storm's macrostructure dictates not just the severity of the weather, but the directional speed and total duration of the threat envelope you have to navigate. Once a storm reaches maturity, its specific hazards map to distinct geographic zones around the cloud. This cross-section illustrates the kinetic threat perimeter. Severe turbulence and massive hail can fall from the anvil into completely clear air. You must maintain a strict avoidance radius of up to 20 nautical miles from the visible edge of any severe cumulonimbus. Inside the cloud, the primary structural icing threat sits exactly here. Severe clear ice accumulates most rapidly in the core of the updraft, specifically in the temperature band between -10 and -30 degrees Celsius, where supercooled water droplets are largest. We also have severe electrical hazards. While aircraft are engineered for lightning, a direct strike can disrupt avionics, cause temporary flash blindness, or even ignite fuel vapors. You must differentiate a lightning strike from St. Elmo's fire. St. Elmo's fire is a luminous purple-blue electrical discharge off the sharp points of the aircraft. It does no physical damage. It simply acts as a visual warning that you are flying through a massive electrical field. Every cumulonimbus generates an invisible hazard sphere that extends far beyond the visible cloud. Pilots must apply strict geometric avoidance parameters based on instrument data. Within that hazard sphere lies the most lethal localized threat to aviation, the low-level microburst. A microburst is a highly concentrated, powerful downdraft spreading violently at the surface. By definition, it is less than 4 kilometers wide, lasts under 5 minutes, and packs a vertical downdraft capable of exceeding 6,000 feet per minute. This split-screen diagram illustrates the aerodynamic trap of a microburst on approach. As the aircraft enters the outflow, it hits a massive horizontal headwind. Look at the indicated airspeed line on the bottom chart. It spikes sharply upward, creating a false surge in lift. The instinctual reaction to an airspeed surge is to pull back the throttles to avoid overshooting the glide slope. This is the exact moment the trap closes. As the aircraft traverses the center of the microburst, the wind vectors shift straight down, violently slamming the aircraft toward the ground, followed instantly by a massive tailwind. The indicated airspeed line plummets, stripping the aircraft of all its kinetic energy. A microburst is profoundly dangerous because the initial wind shift feeds the pilot false aerodynamic data, actively deceiving them into pulling engine power right when maximum kinetic energy is required to survive the ensuing downdraft. To break the microburst trap, commercial aviation developed 2 generations of wind shear detection avionics. First is reactive wind shear detection, integrated into GPWS Mode 7. It continually monitors internal kinematics, like indicated airspeed, pitch, and vertical speed, to calculate wind shear logic. When tripped, it triggers an immediate automated warning: wind shear, wind shear, wind shear. But reactive systems have a critical limitation. They only warn the crew after the aircraft has physically entered the shear, leaving pilots mere seconds to execute a recovery. This side-by-side comparison shows the difference with modern predictive wind shear detection. Instead of waiting to hit the shear, the predictive system projects weather radar forward to read precipitation signatures of a microburst ahead, issuing a warning before entry. If you enter severe wind shear, the escape maneuver is non-negotiable. You apply maximum thrust immediately and pull to the precise target pitch attitude. You must absolutely not retract the landing gear or the flaps. You hold that configuration and accept that your airspeed will decay below your reference speed. The goal is pure energy management to minimize altitude loss. Surviving a low-level wind shear encounter demands absolute trust in automated predictive systems and the flawless execution of a completely counterintuitive energy preservation maneuver. Long before the approach phase, wind shear and thunderstorm avoidance begins at the strategic pre-flight level. The primary regulatory tool for this is the SIGMET, or Significant Meteorological Information. It warns pilots of widespread en route severe weather, including embedded thunderstorms, severe icing, and extreme turbulence, mapping out hazard polygons like the one shown here. For your exam, remember the exact validity periods. Standard SIGMETs are valid for a maximum of 4 hours, while those issued for tropical cyclones or volcanic ash can be extended to 6 hours. Passing Paper 2 and ensuring the absolute safety of your passengers both require the same discipline, respecting the invisible 20 nautical mile threat envelope surrounding every cumulonimbus cloud. Subscribe to Captain Aero to continue your DGCA preparation, and click the link on screen for our next topic, visibility and fog. Remember, in aviation meteorology, what you can physically see out the window is merely a fraction of the danger your aircraft is flying through.